the lunar Farside and its application to 21 centimeter experiments.
Thanks. So I'll begin with a kind of overview of 21 centimeter cosmology. So this is probably going to be a lot of the same things that you just heard from Steve, but it never hurts to hear it again, especially if this is not your field, because this stuff can get confusing. So the 21 centimeter refers to the rest wavelength of the hyperfine or spin flip transition of neutral hydrogen. And so we can use this transition to really probe the neutral hydrogen that existed and the conditions that were present in the early universe. So the rest frequency of this transition is 1.4 gigahertz, but because of the expansion of the universe, the radiation becomes highly redshifted, and so by the time it reaches us, we see it in between about 10 and 100 or 200 megahertz. And because we're looking at a single transition, if we take a spectrum, each frequency corresponds to a different redshift or a different time in the universe. And so you can really read the 21 centimeter spectrum as a sort of history of the hydrogen or the evolution of the hydrogen in the universe. And so in this 21 centimeter spectrum, we expect to see two different absorption troughs relative to the cosmic microwave background. So the first at lower frequencies is the dark ages trough, which corresponds to the time before any luminous objects existed. And at higher frequencies, the cosmic dawn trough, which corresponds to times when the first stars, galaxies, and black holes began to form. And as Steve went into, just last year, the EDGES team published the first ever detection of the cosmic dawn absorption trough. And like he said, this caused quite a stir within the community because the characteristics of this absorption trough were quite different than those predicted by the sort of standard cosmological model as we understood it previously. And so another reason that this detection was so groundbreaking is because doing this, observing the 21 centimeter spectrum, is extremely difficult to do. So in order to see the 21 centimeter signal, you have to look through extremely bright galactic foregrounds. So that's the black line in this plot, which are about 4 to 5 orders of magnitude brighter than the actual 21 centimeter signal that we're trying to see. So fortunately, there are some key differences in the characteristics between these foregrounds and the 21 centimeter signal that we can leverage to kind of pull them apart and extract the 21 centimeter spectrum specifically. And so this is already just a difficult problem of extracting these two different components of the data. But if you're doing a ground-based experiment, you also have to deal with ionospheric effects. So the ionosphere is the upper ionized portion of Earth's atmosphere. And so any sort of radio waves at these low frequencies that we're trying to observe, when they pass through the ionosphere, they're going to refract, they're going to be attenuated, which can contaminate our observations. And so the plot that you see on the right here is the amount of attenuation caused by the ionosphere as a function of frequency. And so this plot only goes down to about 40 megahertz. But you can see that as you decrease in frequency, the amount of attenuation increases. And so the effect is that below about 30 megahertz, which I'll remind you is where the dark ages absorption trough in the spectrum resides, the ionosphere essentially becomes opaque. And so doing these observations from the ground is really not possible. And so as if the ionosphere wasn't a big enough problem, we also have to deal with radio frequency interference, or RFI. So this data comes from, was taken in a location in Europe, which was a possible site for LOFAR, which is another low-frequency radio experiment. And so you can see that below 30 megahertz, there's all kinds of terrestrial radio communications that we're going to pick up with any sort of low-frequency radio experiment. And so this can also contaminate our data. And so the result of all of this is that in order to perform these very sensitive low-frequency measurements, we really need to go to a location that's both above Earth's ionosphere and to a location where the RFI from these terrestrial sources is blocked. And so really the only candidate that's a feasible location to do these experiments is from the moon. And so if you remember back to your first year physics class, when waves hit any sort of boundary, they're going to bend or diffract around the edge of that boundary. And so the same is true for the problem of RFI and the moon. So the RFI is going to bend around the edge of the moon and create a sort of cone behind the lunar far side in which these radio waves from Earth are heavily attenuated. And so I'll emphasize that this is different from the geometric cone, which would be behind the moon, just considering the simple geometry of the system because the Earth is larger than the moon. However, because of diffraction, this region will be smaller in size. And so we really want to get a good idea of how large this radio quiet zone is so that we can get an idea of where we could do these experiments. So unfortunately, this problem of diffraction around a spherical object in the near field does not have an analytic solution, so we really need to turn to some sort of approximation first to try and get an idea of how much attenuation there should be. So the most simple approximation we can make is just simply saying that there's a knife edge or a straight edge at the location of the moon and see how much diffraction there is around this edge. And so this problem was solved analytically a long time ago, but more recently there was a paper published in 2007 which applied this approximation to the case of RFI and the moon. And so here they're plotting the relative intensity of the RFI as a function of angle behind the moon. And so you can see that this middle line here, the dotted line, is 100 megahertz. And so directly behind the far side at 180 degrees longitude, they're saying that there's about 70 dB of attenuation of these radio waves. So that's a good start, but there's reason to believe that this approximation is not a very good one. So for one thing, it's just an edge, so it's assuming that there's just free space behind the edge where the diffraction is happening. And also, it doesn't take into account any sort of electrical properties of the moon, which might affect the amount of diffraction at different frequencies. And so in order to get a better idea, we need to move towards some sort of numerical computer simulation. And so one of the more popular algorithms for doing electrodynamic simulations is called a finite difference time domain method. And so really all you need to know is that the nuts and bolts of this simulation is that we're discretizing Maxwell's equations onto a finite grid. And the way that we do that discretization, we're actually calculating the electric and magnetic fields at slightly offset grid points and time steps. And then when we want to output our results, we can interpolate the fields onto the same grid to make sure that they're consistent. And so I applied this simulation technique to the case of the moon and RFI. So this is a 2D simulation that I did, and you can see that on the left is the RFI coming from the Earth, and then on the right is the far side of the moon, and you can see that just by eye, you can see that the radio waves are heavily attenuated behind the far side. And in order to kind of try to capture the electrical properties of the moon, I took some kind of average values for the properties of the lunar material, and I just used average values because we're really not concerned with how far the waves penetrate into the surface. We're more concerned with their intensity behind the far side. And so we can use these simulations and apply it to the two different cases of possible places we could do these experiments. So the first would be actually to put an experiment on the lunar surface, and then the other would be to use some sort of satellite in orbit around the moon and to do the experiment from there. So these plots are showing the intensity of the RFI as a function of angle for these two different cases, both on the surface and for an orbit 50 kilometers above the lunar surface. And so these are done for a range of different frequencies. And I'll point out that I've put a dashed line at 80 dB because that's approximately the level of attenuation that we'd like to get to in order to do these sensitive 21 centimeter observations. And so you can see that as you move from low to high frequency, the behavior is what we'd expect. So at higher frequency, there's less diffraction, and so the radio waves will be more attenuated behind the far side because they're not bending around the surface of the moon as much. And so the amount of attenuation is becoming greater, and the width of the region at a certain amount of attenuation is becoming wider. And so one final thing I'll point out about these is that you'll probably notice in the labels that these simulations were done for kilohertz frequencies. If you remember the 21 centimeter spectrum, we mostly see it in megahertz frequencies. So the reason for this is that doing these simulations at these megahertz frequencies is extremely difficult computationally because of the amount of grid points that you need to compute. And so we started out at lower frequencies, and although we'd like to push these to higher frequencies in the future, we can really use these low frequency observations to place kind of a lower limit on the size of the radio quiet region, because we'll know it would be at least this large and even greater at higher frequencies. So the simulations that I've shown previously, I just used a perfect circle in the 2D simulations for the moon. However, we know that in reality, the moon has topography and craters on its surface. And so I wanted to investigate how this topography affected the amount of attenuation. And so these plots are similar to the ones you just saw for both on the surface and for an orbit above the moon. But now we're comparing the case where the simulation was done with a perfect circle in this 2D grid and the case where we actually used actual lunar topographical data in the simulation. And so you can see that the effect is small. It's really on the order of about a few dB, but especially above the surface, you can see that craters tend to create deconstructive interference, and so the amount of attenuation is slightly greater, even if it is a small effect. And so I'll finally close out with this projection of the lunar surface, and I've marked out a few different locations which might be possible locations for some sort of radio experiment or radio array on the lunar far side. And I've also marked out a region where we have at least 80 dB or greater attenuation of RFI from Earth at 100 kilohertz. And I'll remind you that at higher frequencies, such as megahertz frequencies, this region will only be at least this large or greater because of the effect of diffraction. And so really what I want the takeaway from this talk to be is that there's a very large region on the lunar surface and behind the far side where there's sufficient attenuation of radio interference from Earth that we can perform these very sensitive low-frequency 21 centimeter observations from this radio quiet environment behind the far side. And I will just put up my conclusions and take any questions.
Okay, the talk is open for questions.
Can't get used to this box. The moon libration, what is it, about 11 degrees or so?
I don't know that I know it off the top of my head, but that could be right.
But that will blur that circle, won't it?
I'm not sure what you're referring to.
You're talking there in terms, maybe I've got it completely wrong. You're talking about straight line view from the Earth, straight line noise, if you like.
Which slide were you referring to?
That
This
one.
one? Okay,
Yep.
yeah.
Is that going to be fixed, or is that, sorry, as the moon librates, that will face noisier parts of the Earth?
Well, I mean, the far side will always face away from the Earth. So,
but it comes around. Come on, Mahaley.
So I think I think this blue circle that is probably fuzzier because of the vibration.
right, sure, yeah, on the edges. I mean, if there's a slight
Okay.
tilting, then yeah, around the edges it won't be a perfect line. It would.
The
be
second question,
fuzzy,
the real
sure.
question I stood up is, Changi 3 or Changi 4 is already active there
Mhm.
on the far side.
Right.
Do you see any implications or any management that should be recommended?
Well, I mean, I certainly think as we move into a era of increased lunar development, we definitely need to be careful about preserving this radio quiet zone on the far side. So that's certainly something that needs to be taken into account, I think, when missions are planned for the far side. But as far as the single Changi 4 lander, I think that it's probably not a significant concern for any sort of surface experiments as long as you're, not right next to it. I'm not totally familiar with the, radio environment of the actual lander and how noisy it is specifically, but certainly moving forward, this is something we need to think about.
Hey, Jason McLean, NASA guy. I just had a quick question. You need the Farside, you also need night time? And if that's the case, how long do you believe you will have to observe to get appreciable signal?
Yeah, so the sun is certainly something that we'd pick up if it was, daytime on the far side. But we're really more concerned with RFI from Earth because it's much more unpredictable, and so it's really harder to model it and remove it from any data than like other sources.
Is your question very short, Mihai?
Very short.
Okay.
How about Jupiter?
Yeah, I mean, Jupiter is the same thing, that we'd also pick it up when it was, in the view of our observations for sure.
Okay, let's thanks Neil once again. And